Hi guys, we're going to give it a minute just to see if there's anybody else percolating into the class. You guys all had a good weekend? Hi. Right here. So 1.6 we're going to do today. It's a pretty short chapter, okay? And then 1.7 we're going to start. 1.7 is actually quite extensive. There's really neat things happening in 1.7. I like to spread it out over several days because there's a lot of stuff going on. And I believe I posted all the classwork for these things already. Okay, so I'm going to do 1.6 and then start 1.7. And then depending on how we're doing for time, then I'm going to break and then we can start working on the classwork for some of these things. Okay, we can start working it through. I believe I've set up, and then we'll just keep going this week. We're going to keep going 1.7, we're going to finish. So we're going to basically do 1.6 today and then 1.7 for the rest of the week, okay? And I believe I've set up, I think the homework for 1.6 and 1.7 and the classwork for this stuff, the homework is going to be due when we have our, we have our exam, which is coming up in another, I think a couple of weeks or so. And then also our classwork for this, I'll take the classwork for these probably close to Monday so that you guys can have it. Also take a look, I'll start posting, getting in the habit of posting some things for you to review from the midterm exam. I'll probably post those at the end of the week. And I'll post those under the section where it says midterm exam. I'll post like review materials for that so you guys can start to see that, okay? So these sections 1.5 to 1.7, we're not going to have a quiz on because I'm going to incorporate them into the exam. Okay, just going to keep that in mind. So make sure that you're taking a look on our modules and our assignments for when these things are actually due. Chapter midterm on 1.1 to 1.7. Yes, so the chapter 1 midterm is all of chapter 1. So it goes 1.1 all the way through 1.7. So it'll be, if you're keeping up with the classwork on stuff, you should be in a good spot, and the homework is a good good way to prepare you for the exam too. But I'll put out some review materials for the exam as well. All right, so let's take a look. Chapter 1.6. There. Okay, so chapter 1.6. Okay, so what we want to do for chapter 1.6 is we want to talk about equations of circles and surfaces. So now remember, this is a math fundamentals class for games. So always we're thinking about like, well, why do I need these equations for my game design? Well, circles form the basis for a lot of things, right? So if I have just a plain old circle, right? Or if I have a three-dimensional circle as our sphere, okay? So I want to talk about a solid sphere or just the surface of the sphere. So we want to be able to think about how we can describe things like circles and surfaces, right? And we need to have equations for those so that we can come up with a definition and we can incorporate them into our worldview, right? It's an important shape to have. Also, when we get into chapter 1.7, 1.7 is really neat because 1.7 is where a lot of this stuff comes together. So in 1.7, what we're going to do is we're going to take all these things and we're going to intersect them with each other. So I'm going to intersect two lines. I'm going to intersect a line and a plane. We'll do things like lines and circles, circles and planes, things like that. So all sorts of intersections. It's all the same methodology for intersections. Okay, but then we're going to cover that in 1.7. So before we get to that, we need to know, how do I describe a circle, okay, and say a three-dimensional circle. So when we talk about, remember we talked about our vector equations, which were also our parametric equations. So these things relied on a vector and a parameter, right? Or just maybe some kind of a parameter to help us describe things, okay? When we talk about things that are implicit equations, these things is where our parameter is implied, right? So there's no parameter because the parameter is implied, which means it doesn't appear in the equation. Doesn't appear in the equation. Okay, so we want to be able to think about what that means. So let's go back to like our graph of like, you know, x squared. So when we talk about parameterization, this is kind of parameterizer. Parameterization. So how do I take an equation and turn it into a parameterized version of itself? So talk about in R2, got y equals x squared. That's just my general parabola. For example, okay, so this is my x-axis, this is my y-axis, my general parabola, okay? So my implicit equation is simply y equals x squared, right? That's kind of our, you know, traditional, what we think of for a parabola, right? Now, if I let x equal to t is some parameter, right? And I plug in t everywhere I see an x, okay? That means I'm going to get y equals t squared, okay? So now a parameterized version of our parabola equation is going to look like this, right? I'll call it x bar as a function of t, right? So this is my xy as a function of t. So I specify, say my x coordinate is t, and my y is t squared. So now I've specified a function in terms of just parameters, t. Okay? So I've reduced it down from 2 variables into 1. It's my single variable, my parameter. Okay. So now I'm going to do something similar for a circle. Also, we're going to start in R2. Remember our generic form of our equation for a circle goes something like this. So I'm going to go x minus h squared plus y minus k squared equals r squared. Now let's talk about what h, k, and r are. So r is my radius of my circle. Right, so let's draw this out. So I'm going to go, here's my circle, like this. This is my x-axis, this is my y-axis. So that's my radius length, okay? This point here that I just did is an x, y coordinate pair of my center. So HK are the coordinates of the center of our circle. We often think about when we're centered at the origin, our circle looks like this. So my HK equals 0, 0, which means my circle looks like this. Right. And then here's my radius value. Okay, so this is my HK. Oh, sorry, my HK. I'm centered at the origin. The equation for this then becomes x minus 0 squared plus y minus 0 squared equals r squared. Okay, so here's our generic equation for a circle. Here's our generic equation, implicit equation for a circle centered at the origin. These both have radius r, right? Radius says r squared, but that's our equation. But our radius value is just r. So now, if I want to parameterize this, I need to think about some stuff. How am I going to do that? Okay. So now let's do this. You guys, I'll give you a second to finish writing that, and then we'll talk about how we represent this as a parameter. Okay. Our parameterized circle, right? Remember, I want to use t as my parameter, right? So let's say I've got my circle. Here's my center, and then here's my radius. And, you know, I'm going to draw it like here's my axis. Okay, now let's think about it like this. Okay, this is also a radius, and I've gone t degrees. T is my angle. T is our angle, right? From some, would be like our x-axis. So this is our origin. Like if you can imagine that I've started off here and I've gone some degrees, this is my angle that I've gone. So t is the angle that we've gone. R is our radius. Okay, this xy is any xy point along the circumference of our circle. Any point along circumference. That's the outside edge. Of our circle. Okay, so now I need to think about a couple things. So what I'm going to do is I'm going to draw a triangle. Okay, so this is these values here. I've made a right triangle here. Okay, so now my right triangle looks like this. You can imagine I've got this sort of like imaginary axis that's going on here. So now I've got a y distance that I've gone, and I've got an x distance that I've gone from my center. So this is my center. My window's open here. It's blowing my papers around. I'm gonna hold these down so they don't blow off. So this is my center. Let's write this as HK. That's our center. Okay. So now what I need to do is I need to think about how am I going to relate my x coordinate to my angle. Okay, so what I'm going to do is I'm going to think my, let's remember our basic trig functions. So my sine of an angle is equal to the opposite over the hypotenuse. My cosine of an angle is equal to the adjacent side over my hypotenuse. Okay, and my tangent, I'll give you that too, is sine over cosine, which ends up being opposite over adjacent. Okay, so our basic, what they call, this is turned into an acronym called SOHCAHTOA. I'll tell you what that means in a minute. So it means sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent, called SOHCAHTOA. Whatever you need to do to help you remember these relationships, you know, of sine, cosine, and tangent, how they relate the angles to the sides of the triangle. Okay, so now what I'm going to do is I'm going to think, right, that my y distance, right, is my y is the opposite to my tangent, right? So this y distance is equal to my sine of t, right? So if I say my y is equal to, let's go like this. So sine of t is equal to y over r. Okay, just based on here, my cosine of t, right? This is my x distance, is equal to x over r. I don't know what y and x are, but I know t and I know r. So I'm going to rewrite this. I'm going to say y equals r sine of t, x equals r cosine of t. Okay, so the sine corresponds to the y, cosine corresponds to the x. Okay, and these are multiplied by the radius. Now, if this is shifted, right, so that my center of my circle is not the origin, my center of my circle is HK, we're going to talk about like these translations, what we call translation in chapter 2. But for now, you can imagine I've moved over, basically I've gone over H distance, and I've gone up K distance to move my center. So then basically my coordinate, how I'm going to represent my circle, goes like this. I would say bar of t, it's a parameter, is equal to, I could say HK plus, right? This is my x coordinate, r cosine of my angle and my y coordinate. Sine of my angle. I can bring this all into one piece, so it looks like t is h plus r cosine of t, k plus r sine of t. And this is a parameterized version of my circle. Okay. So now I no longer need x minus h quantity squared plus y minus k quantity squared equals r squared. All I need is r and t. T is my angle, because what happens is as t changes, right, as t changes, I'm going around the circle, and I'm basically, with every new value of t, I'm generating these x, y coordinates as I go around. Remember, this x bar stands for our x and our y component. Okay. So this is a circle, a parameterized version of a circle. Okay, but we're basically building it out of the radius and the angle. And then we have information like where's it centered, you know, but the angle is the only thing that is changing as I'm going. That's my parameter. I choose those values. Okay. These are, oops, sorry, these are just, you know, equations for you to think about. Oh, this is like debris, but it's really moving my papers around. Hopefully that'll hold stuff. All right. So let's think what happens if we go in 3 dimensions, right? So if I want to talk about, let me just give you, I'll do a 3-dimensional circle is a sphere. Okay, so as I go around in my sphere, I'm just going to be talking about an implicit equation for my sphere, because now in 3 dimensions, right, which angle am I talking about? It's not no longer simple where I can just have one angle that rotates around from 0 to 360 degrees. When we talk about movement in 3 dimension, we're going to go all into detail in chapter 3. Okay, so we use our implicit equation to talk about a 3-dimensional version of a sphere. So I'm going to say x minus, I'll call it a now, squared plus y minus b squared plus z minus c squared, and that's equal to r squared. So what this means is a, b, and c is the center of our sphere, and r is our radius at the widest part, at the equator, at the widest part. Okay, so a sphere, a 3-dimensional sphere, is going to look like my radius. This is my center A, B, C. Okay, so I've gone over A, gone over Y, and I've gone up from my table Z amount, right? And that basically floats my sphere in space, right? So ABC is the center of that sphere, which is one of the reasons why we're only using the implicit equation to talk about it. Because to do it in terms of angles, now I have multiple angles of rotation, but we're going to get to angles of rotation in chapter 2. Okay, so our sphere, okay? Hey guys. I can do functions if I wanted to talk about a parameterized function in 2 dimensions. I can talk about a parameterized function in 3 dimensions. These are fun. If you, I think Northeastern has an account on MATLAB. If you can download MATLAB or use it on any Northeastern computer. MATLAB actually plots things out very nicely in 3 dimensions, and it handles vectors and stuff really well, so you can get a chance to just kind of see what things look like, sort of graphically speaking. But if I had the function x of t, like we said, if this was cosine of t, sine of t, this is a circle with radius equal to 1 and centered at the origin, okay? But if I had it, and this is in 2 dimensions, if I had it in 3 dimensions, say for example, where I had sine of t, and then let's say that I did some kind of, you know, like an exponential function, you know, something else in my 3rd dimension here, what this is going to look like is it's basically going to be a helix. You can imagine it's going to, you know, it's a circle, but it doesn't ever sit on top of itself. It's always, you know, increasing in its value as it goes up. Okay, but like I said, MATLAB will help you visualize. This is just to let you know the dimensional math scales on this as we go. Visualizing it gets more complex. You kind of have to know what these things, I've seen these before, but also it helps to, if you want to plot these things out in MATLAB. Okay, so that's 1.6, just getting you acquainted with circles and spheres mostly is what I was trying to do, and also kind of extending your thought process into 3 dimensions. What would that look like? Okay. All right, 1.6. Okay, now, let's see. Oh, I already, actually, it looks like, oh, so I already did these lecture examples. I'll write these up based on the notes that we just did, and I'll scan those in. I'll scan those in later. Okay, so now we're going to move on to 1.7. Like I said, 1.7, we split over multiple days because there's all sorts of really neat things in 1.7 and we don't want to be rushed. So let's start off with 1.7, part 1. Okay, and it's all the same chapter heading, but I broke it into 3 parts so that you have time to digest it mentally. But 1.7 is intersection, closest distance, and reflection. Really cool topics. They kind of form the heart of all the things that we're trying to do. We're going to pull everything together, and we're going to use these ideas, especially reflection gets used a lot. Reflection and intersection get used a lot in our game environment. You'll see as we work it through. So let's first start talking. So let's do part 1, intersections. We're going to start off straightforward, and then we're going to increase in complexity. So we're going to start off in R2, our 2nd dimension, and then we'll start increasing as we go. So basically an intersection means that we're going to find points that satisfy both equations. Like if I have a line and a plane, or 2 lines together, I need to satisfy points that are shared between both of those objects, right? Equations represent objects, they represent lines or planes or whatever. So these are curves or surfaces. We don't think about a line forming a surface, but we can use a line to denote a hill that's going like this, say for example. Okay, so what this means is I have to solve simultaneous equations, which we can do. We're going to work it through. Okay, so let's talk about some nomenclature, some naming conventions so that we can use those terms. So we have talked about vectors that are parallel. Okay, so things that are parallel, it means, among other things, but primarily it means no intersections. Right, I think of railroad tracks. They're constantly going. They never intersect each other. Okay, I can have 2 lines are parallel if their vectors are parallel. All right, so I've got this vector equation for a line. I take a look at the 2 vectors that represent line 1, line 2. Take a look at those 2 vectors, and I check to see if those 2 vectors are parallel to each other. How do I do that? Are these scalar multiples of each other? All right, so let's say line 1 as a function of t is a plus t times b. Line 2 as a function of t is b plus s times w. A and b are points on line 1, points on line 2. So this is, I can really write this as a vector because it's an xy pair. V is the vector parallel to line 1. W is the vector parallel to line 2. We have different parameters, s and t, for 1 for each line. Okay, so if v is parallel to w, they're scalar multiples. Right? Okay, so those are lines. We can talk about planes. So two planes are parallel if their normal vectors are parallel. We kind of talked about this before, right? So this is line 1, this is line 2, this is, let's draw our pictures. So this is V, W. I'm really exaggerating those vectors, right? So if I've got two planes that are parallel, plane 2, there, I'm going to have normal vector normal 1 coming off of here, right? That's perpendicular to that. Normal 2, it's perpendicular to this plane. Okay, so now we're looking at two planes. Each plane has a vector that's normal to that plane. We check if those two normal vectors are parallel, because if the planes are parallel, the normal vectors will be parallel. So plane 1, I can denote as A x1 plus B y1 plus C z1 equals D. My plane 2 is E x1 plus F y2 plus G z2 equals H. For lack of better variable names, you can choose whichever variable you want. I extract out my normals. The normal for plane 1 are the coefficients for x, y, and z. My normal for plane 2 are the coefficients of x, y, and z. Right? And I check to see if if they're parallel. Are they parallel? Are they scalar multiples, right? Okay, so that's how I'm checking my normal vectors. Okay, so you guys, I'll let you guys finish writing that, and then I'll turn the page. Okay. Right. So let's also talk about what it means to be not intersecting but not parallel either. So that's going to happen with our lines. Okay, so I can say in R2. In R2, our lines, if they are not parallel, just in R2, if they are not parallel, then they must intersect because we're in 2 dimensions. If they're not parallel, then they must intersect at a point. Okay, so I've got line 1, I've got line 2. This is our point. This is going to be an x, y coordinate point of intersection. Okay, between these two here, right? Now it gets more complex because in R3, I can have lines in R3, okay? R3 is my 3-dimensional, but I can still have a line in R3. Now, in R3, if the lines are not parallel, okay, one of 2 possibilities can happen. They can intersect, or they can be what we call skew. We're going to talk about the first one. So they can be skew, which means they don't intersect because they actually lie in different planes, don't intersect. But they're not parallel, so let's draw that out. So I'm just going to represent my 3 dimensions as some kind of a cube. Okay, so here's my 3 dimensions, right? And I've got line 1 cruising right along, you know, parallel to this edge of my cube. And I've got line 2 cruising right along right behind it. You can see, here's line 2. Right? It's never going to intersect line 1. They happen different from each other. So line 2 is going up and down, line 1's going back and forth, but they're not ever going to intersect each other. This is called the skew line. We're going to see what these things look like mathematically, but just for concepts, right, what it looks like, you know, sort of graphically. So line 1 and line 2 are on different planes in R3. Therefore, do not intersect, but are not parallel. So in R3, you know, you can do a check. Are they parallel, yes or no? Okay, if they're not parallel, now I have to check to see if they intersect or if they're skew. So in R3, things get a little more complex, but that's fine. Okay, so that's a skew line. Now, if they're not parallel and they're not skew, then they're going to intersect each other. So I can even write R3 up here. So they could intersect each other in a point, right? So this could be an X, Y, and that's in R2, or X, Y, Z in R3. Okay, so they can intersect or they can be skew. We're going to see what that looks like. Okay. So let's do example 1 on chapter 1.7. All right, so we've got these two lines. Line 1 is, right, should be, did I write this? Okay, yeah, so this is a parameterized version. So this is line 1 of t equals this whole thing here. So this is our point plus a parameter times the vector. So this is our vector parallel to the line. This is an implicit equation of the line. We're going to talk about how we check to see intersections when I have a parameterized, a vector equation for a line, and an implicit equation for a line. We can do it for other types, other ways. Just the math is just slightly different, but we're going to focus on this stuff for now. All right. So now what I need to do is I'm going to take my L1, my line, and I'm going to break it into my parameterized, break it into X, Y components. Okay. So I say my X is equal to all of my X components. So just like we did before, 3 plus 2 times T, right? I pulled out just my X components. I'll do that for Y, minus 2 minus 1 times T. I'm going to take these X and Y, and I'm going to plug into L2, X and Y. Okay, so now I'll have this equation, but in terms of simply T, right? So let's do that. So I'm going to get, so L2 is X plus 2Y equals 3. So into X, I'm going to plug 3 plus 2 times T. Into Y, I'm going to plug minus 2 minus T. Okay, and I'm going to solve for T. All right, so let's do that. So I'm going to go 3 plus 2 times T plus 2, don't forget your coefficient of Y, minus 2 minus T equals 3. Right, all I did was plug L1 into L2. And now I get to solve for T. Depending on what happens with T, if the T's cancel, if the equality is valid, if the T doesn't cancel, I'm going to be able to tell whether things are parallel, if they intersect, and in R3 I'll tell if they're skew. Okay, so now let's do this. So I'm going to get 3 plus 2 times T, plus I'm going to distribute. So a minus 4 minus 2 times T equals 3. Oops, watch what's happening. 2 times T minus 2 times T, the T's cancel. So the T's cancel. That's my first clue that the lines are not going to intersect. T's cancel, lines do not intersect. Okay. If the T's do not cancel and I solve for T, which we'll do later, right, then I can actually get an XY coordinate for where things intersect. So we're starting off with a negative example. These things do not intersect because the T's cancel out. Okay, so I can say, let's do this. I'm going to add these up. So this is going to become 3 minus 4. So minus 1 equals 3. It's not true. So these lines do not intersect. Do these lines intersect each other? No. Okay, because the T's cancel out. Okay. Incidentally, let's just take a look. I just want to take a look at my line equation. So my line 1 has a vector equal to 2 minus 1. my line 2, this is the vector parallel to the line. Right? It looks like this, right? So this is my V. Okay. Line 2 has a vector normal to the line. Remember, in implicit equation, our vector is perpendicular to that line. So I extract out my components, positive 1. Ooh, they look similar, right? So that means I've got line 2, line 1. This here is 1, 2. Let's do this. If I take this here, if I take this here, and remember our trick for finding a vector that's perpendicular to this one. So let's see, perpendicular to, I'm going to switch the x and the y, and I'm going to negate the new y. Look at that. So it's the same vector. That means that these lines are actually parallel to each other. Right? Because the vector on this line, 2 minus 1, is the same vector that's on this line. These lines are parallel. But it was a trick. You couldn't see it because this was written in implicit form, which has a vector perpendicular to the line. This is written in vector form, which has a vector parallel to the line. So we tricked you. But you would see it here because the t's cancel out. And then just to cross-check it, you can see that the vectors are the same. All right. Example 2. Okay, so example 2 looks like this. I've got 2 lines. We want to know if they intersect each other. All right. So I'm going to do the same thing that I did before. I'm going to take this one and break it down into components and plug it into here. So line 1. X equals 3 plus 2 times t. Y equals minus 2 minus 1 times t. Okay. And I'm going to plug into L2. So it's going to look like 3 plus 2t plus 2 times minus 2 minus t equals a minus 1. Okay, let's see what happens. So this is 3 plus 2t minus 4 minus 2t equals minus 1. All right, well, still, I see an alert. Minus positive 2t minus 2t. The t's still cancel out. Okay, in this case, I've got minus 1 equals minus 1. Okay, so these lines again also parallel. Okay, they overlap each other, right? My equality is good. The lines are sitting right on top of each other here. Okay. Whew. All right, let's do example 3 so you can actually see a point of intersection on these 2 lines. Example 3, we've got these 2 lines. Do these lines intersect? So let's do the same thing. So line 1. So x equals 3 plus 2 times t. Y equals minus 2 minus 1 times t. I'm going to plug into L2, and I'm going to get 3 plus 2t plus 3 times minus 2 minus t equals minus 1. Okay, now I'm going to multiply all this out and do it over here. So I'm going to go 3 plus 2t minus 3 times minus 2 is minus 6. 3 times minus 1 minus 3t equals minus 1. Okay, look, my t's are not going to cancel out this time. So 3 minus 6 is minus 3. 2t minus 3t gives me minus 1t equals minus 1. So I'm going to bring the constant terms over. So I'm going to add 3 both sides. So I'm going to get minus t equals positive 2. I'm going to divide by negative 1. So t equals positive 2. Did I do that right? I'm sorry. T equals negative 2. I can multiply. All right. T equals negative 2. T's did not cancel out. That means that the lines intersect. Therefore, our lines intersect. Now I want to know, at what point do they intersect each other? At what point do they intersect? So I use the t that I just found and I plug it into my L1 components and I get my x, y coordinate of the point of intersection. Let's write that down. Use t just found, plug into L1 to get x, y coordinates of intersection point. Okay, so let's go ahead and do it, right? So let's write that down. X equals 3 plus 2t, y equals minus 2 minus t. I'm going to plug in my t. Okay. So I'm going to get x equals 3 plus 2 times the minus 2. Y equals minus 2 minus 2. So 2 times a minus 2 is minus 4. 3 minus 4 gives me minus 1. Minus 2 plus positive 2 gives me 0. So the point of intersection equals minus 1 comma 0. Okay. Let you guys finish writing that. And then we're going to do intersection of a line and a plane. Same process. Now I've shown this to you where a line, one line is in parametric form, vector form, and the other line is in implicit form. Okay. If they were both in the same form, both in vector form, I would have to set the x is equal, the y is equal to each other, and then solve for t. That way I'd have two equations and one unknown. If they're both in implicit form, I'd have simultaneous equations where I would have to solve first for x, plug it in, and then solve for y. We tend to focus in this class on examples like this, where one's in vector form, one's in parametric form, and it's easy to substitute. It is possible to do it the other way too. We do that a lot more in linear algebra. All right. So, do the line and the plane intersect each other? And if so, at what point? Okay, so let's take a look. So I've got my plane that's in implicit form, and I've got my line in parametric form. I can do the same process that I did before, where I'm going to take, see, let's draw this out. Like, so our question is this. Here's our plane. Here's our line. And I'm going to put a question mark. Is that true? Is that happening? Like, at what point is that actually occurring? Okay, so the same process that we did before. I'm going to take my line. I'm going to break it down into component pieces. So notice I'm now in 3 dimensions because my plane exists in 3 dimensions. So a line in 3 dimensions needs x, y, z. So x equals 3 minus t. Y equals 0 plus t. Z equals 7 plus t. I'm going to plug this into the plane. And then solve for t. Okay, so let's do it. So I'm going to plug in 3 times, so my x, 3 times 3 minus t, plus 2 times y, t, plus 5 times z, 7 plus t, equals a minus 4. This is my plane equation. This is my x, this is my y, this is my z. I plugged in my line into my plane, and now I have to solve for t. So let's multiply everything out. So I get 9 minus 3t plus 2t plus 35 plus 5t equals minus 4. I'm going to combine like terms, right, and then see what I get. So minus 3t plus 5t, minus 3t plus 2t gives me a minus 1t. Minus 1t plus 5t gives me 4t. So I'm going to go 4t. 9 plus 35 is 44, and that's equal to minus 4. I'm going to subtract 44 from both sides. So I'm going to get 4t equals minus 48. Solve for t by dividing by 4. So t equals minus 12. All right, so a couple things, right? our t's did not cancel. If our t's canceled, then the line and the plane lines are maybe sitting on the plane or it's parallel to the plane somehow. If they don't cancel, I get a valid value for t, then that means that my line and my plane intersected. Yes, intersection. Okay, now I have to find the point at which they intersect. Okay. Find point of intersection. Just like we did with the two lines, I'm going to take my t and then plug it back into here and find my x, y, and z coordinate of that point of intersection. You say x is equal to 3 minus 12. Y is equal to minus 12. Z is equal to 7 plus or minus 12. Okay, so 3 minus a minus, 3 plus 12, that gives me 15. Y equals minus 12. 7 minus 12 gives me minus 5. So my point of intersection is 15 minus 12 minus 5. Okay. Okay. What do you guys think? Kind of a lot to take in, but it's pretty cool stuff. We're talking about intersections here. Okay. Let's do I'll do one more example and then we can break a little bit. So we're gonna do and I think what I'll do is I'll start uploading. I'll scan in the 1.7 stuff that we have today, and I'll just do 1.7 part 1, part 2, part 3, so that you guys can have the 1.7 examples in the meantime. So you guys remember Angry Birds? It was really popular, you know, a couple years ago. So what's the intersection of the bird and the hill given the two equations? So the bird, right? So let's think we've got this. And here's our ground. Right, my hill equation, this is just a straight line. Here's my hill. And my bird is gonna go, like we launch the bird and it goes, whoa, flies out. This is my bird. Right? So our bird is a parabola and our hill is a straight line, right? And we reference this as a ground just to make it look nice, right? But this is basically what's happening, right? I've got this object here, you know, a bird, right? That's flying through the air, but it flies through the air on this trajectory and it's going to hit the hill. And we want to know where it's going to hit the hill, or, you know, does it not? Does it fall short of the hill? We'll figure out that whole falling short thing later. Okay, so we've got our hill equation, we've got our bird equation. So same thing that we've done, right? I'm going to break this into x and y components. So from the bird equation, my x and y components, x equals t, y equals 4t minus t squared. I'm going to plug that into my hill equation. Right, so my hill equation goes 3 times x, 3 times t, minus 2 times y, 4t minus t squared, equals 3. Distribute, and then solve for t. So that's going to become 3t minus, this is 8t minus 2t squared equals 3. So let's bring it all together. So this is going to look like I need to subtract over this minus 3, and I need to combine these two terms here. So then this equation ends up looking like, let's write it out like, go the other way. I'm going to write it like this: 2t squared minus 5t minus 3 equals 0. Okay, so however you want to take a look at it, right? I'm going to do quadratic formula. Okay, this is actually this is minus 2t squared because it's minus 2t minus 5t, and I bring the 3 over. Okay, so quadratic formula or factoring, however you want to do it. Quadratic formula, remember your quadratic formula goes like this: minus b plus or minus square root b squared minus 4ac over 2a. There's some great mnemonics for remembering the quadratic formula. I think I give it to you when we on the test. If I'm asking you for the stuff, or on a quiz, I'll give it to you. But if you want to remember, a quadratic formula is very helpful for finding this stuff out. Anyway, and after I factored it out, I find that t equals, so this is a equals -2, b equals -5, c equals -3. These are the coefficients in my term here. So when I do this with my quadratic formula, I'm going to get -1/2 and 3. This is time, actually, right? Because it takes time for it to travel. The negative doesn't make sense, right? The negative is like, you can imagine, so my lightly, and imagine my Hill equation comes down and my parabola comes down. That would be my negative. So this is -1/2, and this here is 3. Okay, so we can discard the negative one. It doesn't make sense for what we're trying to do. So t equals 3 is the value that I'm going to be using here. If you had two positive values, say for example, like if we have, say, a circle and I've got a line through it, I'm going to get two positive values. Okay, so what that means is I need to find the value closest to me, okay, closest that the line is going to hit first. And we're going to talk about that closest distance is how you would think about that. We haven't gotten there yet. Okay, so we'd say at time t equals 3, the bird hits the hill. Okay, now I need to know where. What's the, what coordinate? Okay, at what coordinate is it going to hit the hill? So I'm going to use my equation, my x equals t, y equals 4t minus t squared, and I'm going to plug in my t equals 3 to figure out what that is. So this is going to become x equals 3, y equals 4 times 3 minus 3 squared. So this is 3. 4 times 3, that's 12, minus 9. That's equal to 3. So 3, 3 is our point of intersection. Okay. There. So we'll end on that example. I've got some other examples for like a line and a plane and all sorts of stuff, but I want to end there so that you can kind of let it sit, think about it. Okay. So for the next, 5-10 minutes or so, I'm going to start working through some classwork stuff. Okay. I'm going to take a look first at my 1.6 classwork, and then I believe I printed out my 1.7 classwork. I'll do some examples on that too. Okay, I'll leave that for just a second while I'm getting my classwork for 1.7. Okay. Pull that up for you. And there's a lot of stuff on this page for 1.6. Don't sweat it. Do a couple problems on there. It's just to get you thinking about how do you plot a circle given an equation, or if you're given certain parts of it. I'll do a couple of these things here. Don't worry about some of the bottom ones. It's or if you've got a diameter that kind of helps you think about it too. So help you plot the parabola, so that you can kind of think about things, parametric versions. It's just to kind of get you thinking about how you look at this stuff. But don't feel like you have to do all of it. Just do a few, like maybe, three questions, 3 of these. It'll help you. I'll do some so you can see what it looks like. So this one, my radius is equal to 3 because this is my r squared, and my center is equal to, remember, it's x minus h, y minus k. So my center, this is going to be -2, +1. It's always the opposite sign from what you see in the equation. So that means I'm going to go -2, +1 is my center. Now for radius 3, what I do for that is I go up, north, south, west, and east in 3 directions. So I go 1, 2, 3, I put a little dot, 1, 2, 3, I put a little dot. That gives me 1, 2, 3, I put a little dot, 1, 2, 3. That gives me like a I'm not a great artist, but you get the idea. It gives me places that I can draw. It kind of helps me visualize what my graph looks like. Okay, so same thing here. So my radius here is equal to radical 5. I'm taking the square root of this. My center is equal to -3, -4. It's opposite sign from what's in there, right? So radical 5, so radical 4 is 2. So radical 5 is just a little bit more than 2. So I'm going to go 1, 2, 3, 1, 2, 3, minus 3, minus 4. There's my center. I'm going to go up just a little bit more than 2. So 1, 2, and a little bit. 1, 2, and a little bit. 1, 2, and a little bit. 1, 2, 1, 2, and a little bit. So that kind of gives me an outline. Okay. You know, you're not going to go overboard on these things here. Just going to give you a way of reading this. So my radius here is equal to 1. My center is equal to 2 minus 3. Same thing. Okay. Now they're telling us to graph it. So if my center, I didn't scale this, my center is at minus 13, minus 14, and my radius is 1, it's going to be like this. You know, my center here, my area, remember area is pi r squared. So this is r squared. So my radius is equal to 4. So if my center is here and my radius is 4, my circle is like that. And this is just kind of thinking about how you don't worry about the tangents or the diameter, just a way of thinking about our equations for our circle. Parabola is the same way, right? I can go up if I'm not sure. There's like a form. The negative on the outside means it's pointing down like this, right? This tells me these are like the points, either the maximum or the minimum on my parabola. So it's going to be minus 3, minus 1. So if I go minus 3, minus 1, and this thing points down, it's going to go like that. These are just some things that like we learned in algebra 2, maybe, you know, thinking our algebra 1, thinking about like how do I graph parabolas just from these vertex forms. And this, you know, same thing here. It's kind of like what we did here. So this is pointing down as well. That's what this is, right out in front. It's going to be minus 2. So then my y, my x coordinate is let's see, 2 minus 2, and it points down. So 2 minus 2, and then this thing points down. It's just to give you a feeling for like how do you plot these things out. Okay, so that's just chapter 1.6. So don't go hog wild on the 1.6 classwork, just to kind of get you thinking about how these things look. Okay. Right, so I'm looking at, this is my part 1, chapter 1.7 classwork. I'll do, I think I've got time to do like the first problem. Show that the line is parallel to the plane without explicitly showing that there are no points of intersection. So I'm just gonna, I like to sketch. So here's my line. And I've got a vector. So my vector, it's because it's a vector form, right? So that means my vector is minus 1, 1, 1 is my vector. And I've got a plane like this. Here's my plane. And then it's the implicit form of my plane, which means that the normal to the plane is equal to 3 minus 2, 5. I just got that from my coefficients for x, y, and z. Now, if the plane is parallel to the line, and this vector here is perpendicular to the plane, then this vector must be perpendicular to the line, right? So there's some process that I can use that'll show me that two vectors are perpendicular to each other, and that is the dot product, right? So if I say v dot n should be equal to 0 if v and n are perpendicular. If v and n are perpendicular, that means then my line is parallel to my plane. So let's go ahead and do the dot product. Minus 1, 1, 1, dot 3, minus 2, 5. Dot product means I'm multiplying corresponding components together and adding them up. So it's going to look like minus 1 times 3 plus a 1 times minus 2 plus a 1 times 5. Minus 3 minus 2 plus 5 is equal to 0. Okay, so that means that the vector and the normal are perpendicular, which means that the vector that's parallel to the line is parallel to the plane. Therefore, line is parallel to the plane. Okay, so I didn't have to go through it to check to see if they intersected each other or not. I could just do a quick check on the vectors that are important to these lines and planes. Okay. All right, that's all we have time for today. I'm not supposed to keep you past. And then when we come back on Wednesday, we'll keep working on 1.7. and we'll keep working through the classwork for these things, okay? Bye, guys. Have a great day.